Okay, and you want to. I won't spend too much time on this slide, but everybody understands the basic concepts of trophism, where you get the primary productivity plants, algae, deep sea thermal vents. Essentially, you're not using PAR, photosynthetically active radiation, but lithoautotroph. So it's another form of metabolic pathway, but still one that is, you're getting energy from somewhere, you're getting carbon from somewhere, and you got to have an exhaust gas, electron donor, carbon source, and your electron acceptor. So it's the metabolic triplets. Secondary, us, animals, bacteria, fungi, archaea. You're going through the primary pathways of life there, or sorry, the three kingdoms, excuse me. And you've got that 1/10 energy transferred. So it's within the systems that I'm working with, the growth matrix that engenders that is the attachment surface area for the biofilm that is growing and self-organizing and self-selecting within the reactors. I'm essentially cheating. I'm using a plant fiber, usually either hemp or straw, but my main thing is lignin-based coconut coir. It's called coir. You break up that coconut and you got all that material, those threads. That is the best darn stuff I have ever come across to be a surface attachment area within a bioreactor. It lasts for an incredibly long time, and I'm not even joking, like decades in some cases, because it is not itself a carbon source of the within that reactor. So it's unused. It's essentially like plastic. It's also a loose fiber matrix, which means when you drain the darn thing, it all collapses and then it refills and maintains its loft. So if you think like anybody likes to go camping, you think about the loft in your sleeping bag, where you want it to have that dead air space. You want that loft. You want that coir to fill out 95% of the space within that particular reactor, because then when you empty it, it collapses itself. You can wash the material clean, whether it be aluminum, iron, or manganese in some form of oxide, and then just refills itself. And all you have to do is stir it, empty it, and then just close the valve and let it fill again. So it's a very simple system. Usually it only takes me about 2 hours per month to clean the one system of the reactors I showed you there on slide 1. It only takes me about two or so hours, which is good because that means it's cheap, which means I get to sell more. I haven't sold a whole lot of them, but they work better and better. It's an iterative process. Anyway, sorry, I was diatribe there. And then the tertiary, but I mean, you get the idea. Basically, what I really wanted to focus on is that this system, as I'm using them, relies on primary productivity to create a growth matrix. But after that, you don't need it at all. And essentially, the system could be entirely aphotic and it would not matter. You don't need sunlight to run these systems because the energy is based off the chemistry and the biology, and how the biology then manipulates the chemistry to clean the water by sequestering each one of those particular, the final products, the waste products, which are low pH iron or manganese. We think manganese. We're still working that one out. Aluminum is abiotic though, but still is what's I would call indirect bioremediation. But yeah, I'm gonna move forward here. A little easier to think about it when you're looking at the boxes. So that in practice, if you look at the one with the corner on it there, the one to the left side, if that particular system right there, those 8 boxes, if they were capable of remediating the entire system, and they were capable of both being aerobic and anaerobic. So you start off aerobic, you pull out all the iron that you possibly can, and then you go to anaerobic, and then you start manipulating salt. Then you're trying to get down to, say, sulfate reduction. By driving off the hydrogen sulfide that comes off of that, you've manipulated the pH within the system, because you're essentially driving off the acidity, that HS2, well, the H, that hydronium ion, yeah, the H, not the OH, yeah, because the OH is the alkalinity, but I think it's a hydronium. No, doesn't matter. You're driving off the acidity, okay? And then when you reoxidize, you now have a pH. This is hypothetically. This is what what we're attempting to prove at the next step. So I'm kind of giving you a preview on what my continued our continued research is to be able to, without adding alkalinity, like limestone or caustic soda or slaked lime or hydrated lime, without having some exogenous alkalinity source that what's using already in the water. For instance, average sulfate in mine drainage is like 2,000 parts per million or 2,000 milligrams. It's a lot. You wouldn't want to drink that. Anything over 250 parts per million will give you gastric distress. So you definitely don't want to drink it. But it also gives you an opportunity here to provide an electron acceptor that then manipulates the pH once it goes to aerobic again. Now it's hydrogen sulfide. I don't have to tell anybody out there that that stuff is really dangerous. So you have to be able to properly capture that material, that gas. Now, in the context of ISRU, you also have a potential now of creating sulfuric acid, which is really, really useful. I mean, that's one of the keystones of any industrial chemical process. So you're starting with a biological process to try to do one thing, and then that byproduct could then potentially be used as a feedstock for something else, or to return it to the pile, so to speak. I mean, if you're talking about ISRU on Mars, now you've got essentially, I mean, it's not truly free conservation of energy and mass, and what it costs to get the material, the equipment up there, but you would have a way of generating something that could then spool up and exponentially spiral up your abilities to process more regolith in the long term, which is going to be pretty important because you can't necessarily take it with you. Maybe a tiny bit, but you want to have the knowledge and the basic equipment in order to be able to do it once you get there. And it doesn't necessarily mean that you have to do sintering or when we're baking different regolith in order to begin to break down the process for additional processing. You can do a lot of it here. I mean, for instance, pretty much all the copper that we still get to this day is, it's heap leach process. But you got to get that sulfuric acid from somewhere. Well, here's a potential means. Hypothetically, once again, I haven't necessarily done this, but we all know that this occurs in nature all the time. It's happening in your bellies right now. I won't get too much into it, but you get the idea. Let's see. Yeah, I kind of talked over some of that stuff. We're still trying to figure out whether the manganese that we're getting out in our systems, because we had exponents, or we had material and rates that were coming out on average 2 exponents better without the addition of alkalinity or limestone than is normally seen in acid mine drainage treatment systems. We're still trying to figure out if that is just some extreme abiotic process or if it is in fact a biological one. My money's on the biologic, but we're still waiting on more data and just the funding to be able to do a greater deep dive on the metagenomics. Anecdotally, so far we're hearing no, but then I know that there was a paper published by you and Ledbetter talking about manganese oxidation, biological manganese oxidation in the presence of a small amount of strontium, I think it was, which is something we had seen at one of our other sites. So we think it is. Why that could be important is because if we can show that manganese is both oxidized and reducible by microbiology in an open environment, then that gives us a whole bunch of capacity to, you've got all this, the cation exchange and the reductive potential of manganese, which is highly, highly, highly useful. For instance, manganese is added to all batteries to halt the polarization of the anode, I think it is, which increases the efficiency of a battery and stops it from having an electrical loss as it's being used. Essentially, polarization, you get a whole bunch of molecules in and around bubbles, essentially in and around the one of the electrodes, and then it halts the passage of the electricity through that, that what it is a abiotic redox pathway within your batteries. I mean, you don't think about it a whole lot, but the standard lead acid battery, every single one of them has manganese oxides in it. Um, won't get too much into that right now. I just really like manganese. It's some neat stuff. A lot of potentials there. Rare earths, especially, is, well, I won't get into that right now, but you can ask about it later. Okay, so we also, so there's the mining, but there's also, this same process applies to oh, good old fashioned food waste processing. Because if you're going back to just good old fashioned aerobic metabolism, everybody there is eating food. And that's that's both your electron donor and your carbon source. We've got one of those slightly strange metabolic pathways where you get a twofer versus, you're breathing the oxygen. That's where you're getting your 30 to 32 ATP. It's a very efficient, very powerful essentially biogeochemical pathway. That's why we're as big as we are. So in this system here, those are some of my older units. They were out at a mining site. Didn't work out all that well because, you're going to have some losses too. I didn't know how to plumb the darn things back in the day, going back to 2015. So we pulled them and I figured out the actual size of the pipes that we need to run at a system that is really useful, because it turns out you really want to run them faster than you think. If it's aerobic, you want good oxygen saturation. You want to be able to really get everything mixed and stirred. And I'm starting to lean towards, I think there's also a benefit of having just the flow pressure of the water moving through the system, as opposed to like a bubble lift system, which I've also tried. I'm not really happy with, though. I think that a positive pressure of water moving through the system is of benefit beyond just oxygen availability and saturation. I don't have any evidence for that yet, though. That's another one that we're trying to figure out. There's a lot to learn here. But essentially why that's important is going once again back to ISRU, or, say you're up in the ISS. Are you going to continue to just keep dumping everything overboard and having to bring it back up? Or are you going to have an even more effective ECLIS system that allows you to recycle more material, not necessarily all, but if you can recycle even more material while it is up there, water's heavy. I'm not telling you guys anything you don't already know. And you have these potentials of, say, sulfate reduction to produce hydrogen sulfide. Dangerous, yes. But it's still something that is easily taken care of here on Earth. In methane production, a lot of times you're going to have hydrogen sulfide in that gas stream as well, and you got to get that hydrogen sulfide out. You don't have to, but if you were ever going to really intentionally inject it into a pipeline, hydrogen sulfide, like I said, it's nasty. It isn't just deadly to us. I mean, that'll corrode pipes. And then that corrosion obviously is going to wear down the pipeline. So essentially using a system like this based off the principles that Winogradsky had developed, you have an opportunity to biologically distill, drive off all this hydrogen sulfide first, so that when you're left with the methane, you might not necessarily need to do much in the way of screening and filtering of that gas stream. There's an additional benefit that, maybe you're going to have even greater concentrations of CH4 versus CO2, because those are usually the two other byproducts. Let's see. But importantly here is, if you're thinking about, I've heard it called a biological Schenck line, but a biological distillation process that allows you to sort out all these materials by just running water through a system. Now we're working on developing some conceptualized formats and structures for doing this 0G as well. Now it's a big ask, but with the team that I'm proud to be a part of with Arcology X, and maybe some people who are listening to me right now sitting out there might be able to offer some ideas or point us towards some literature that may help in our goals of developing a system that is good for either 0G or lower gravities. I mean, obviously we can do it here. I figure we can do it on Mars or the moon, but 0G or microgravity, I should say. That's it's mostly you just don't want a bunch of water everywhere. I mean, it seems pretty obvious, but it does give us a lot of potentials for saving an enormous amount of energy while also providing a whole bunch of new unique products that otherwise we would have to send up.